Welcome back. In this video we're going to begin our discussion of atomic theory through the course of several, about 4, 5, 6 videos. I'll break it up into smaller chunks. The overarching theme in this next set of videos is going to be the development of atomic theory. In other words, we're looking at the model of the atom from the beginning up to the point where we pretty much have it today. We're going to stop at the quantum mechanical model, which has been improved on greatly, but that's where we're going to stop in high school. So this video, we're going to start at the very back here at the ideas put forth by Dalton in the early 1800s. So that doesn't mean the idea of atoms was just invented by Dalton in the early 1800s. The idea has been around for a very long time. There were philosophers in ancient India, the Middle East, and I'm sure there were in China as well. The one that we tend to focus on is Democritus, because we are Western civilization and the Greeks were considered the forefathers of Western civilization. Democritus is the Greek who is attributed coming up with the idea of atoms first. You know, it wasn't earth-shattering. You've all probably thought about it as a kid. What if I take this stick and just keep breaking it in half? How many times can I half the stick and still have something? And Democritus was one of those people who sat and thought about that same problem. And he eventually came to the conclusion that at some point he would get to a smallest possible particle that kept the properties of the stick. And he called it atomos, and this on the slide here is atomon, which I think is plural, but atomos means indivisible. And so that idea was not taken very positively by the other ancient Greeks. Even some of the foremost ancient Greek philosophers like Aristotle did not accept Democritus. A few people did. It wasn't like he was laughed out of town, but they prefer to think of the elements as earth, fire, water, and wind, that sort of stuff. So the idea of the atom sort of fell by the wayside for about 2,000 years. And then some experimentation started happening after the Renaissance and then into the Enlightenment era, where alchemists and then later chemists and biologists and really all the scientists really were doing experiments to try to answer some basic questions. They would make observations about nature and then they would experiment more to find the answers, or at least develop hypotheses about what the answer might be. So one of the observations that they came up with was that when you looked at certain particles under a microscope, which was itself a fairly new invention, like pollen grains, they seemed to dance around. They were jiggling around, which would be something that happened to living beings like protozoas and things like that. But pollen grains are not alive. They shouldn't be moving around. And so a lot of questioning and experimentation went into this. One of the big experimenters in this area was a Scottish botanist named Brown, Robert Brown. And his idea was that there was a property of the fluid, these some particle motion that we couldn't see, that were always in motion, and these particles were probably striking the pollen grains and other things he saw. By the way, he did this experiment on a lot of things other than just pollen. And so his idea was that maybe there's something there that we can't see jiggling this around. Well, then that set off about 100 to 150 years of pure mathematics, with people trying to come up with a model that would explain that. And that was eventually done by Albert Einstein in 1905. But here's the bottom line. Brownian motion proved the existence of atoms. And we'll look at how it proved it as we talk about Dalton. But for now, let's take a quick look at this couple minute video here on Brownian motion, just to give you a better idea of what it is.
In this lesson, we're going to have a look at the idea of Brownian motion. This is useful because it helped indirectly to confirm that atoms exist. You're in a darkened room, the air is still, and the bright lights are streaming through the window. What do you notice about the dust particles? The black circles as they pass through the beam of light. Pause the video and think about this. Press play once you've made up your mind. The answer is that the dust particles are moving randomly. Did you see it? The dust particles are not always moving downwards, but are moving in all directions. The dust particles are very small and are supported by a fluid. In this case, that fluid is a gas. You are unable to see the gas particles directly because they are too small, but you can see the larger dust particles. The reason that the dust particles move randomly are because of the gas. We know that the gas is there because every time we move our hand through the air, we feel them against our hand. Try it now. Continue when ready. The particles in the air move in random directions quickly. This means they will have many collisions or will bump into the dust particles many times. Each collision between air particles, very small coloured circles, show how the dust particle, the black circle, moves off in a new random direction. It's a bit like a game of snooker, where there are millions of marbles which collide with larger, observable particles like a ping pong ball. This effect was first observed by scientist Robert Brown. He was looking at pollen grains suspended in water under the microscope, and he wondered why they jiggled around. He thought that the pollen was alive. It was later that scientists realised the importance of his discovery. Now, here's a challenge for you. Thinking about what we know about dust particles, can you explain why the pollen grains appear to be jiggling randomly? Pause the video and continue when ready. In summary, the fluid is no longer a gas, but is a liquid, water. The pollen grain is colliding with many water molecules. Each water molecule is too small to see, but we can see the combined effect of their collisions on the pollen grain as it moves randomly. This effect is known as, you guessed it, Brownian motion.
Alright, so that was a good animation, hopefully to highlight some of the things I just said. But before we leave this slide, Brownian motion was important because it gave some experimental credence to maybe there's something smaller than we can see that actually is matter, and it can interact with larger pieces of matter. So that takes us to John Dalton. Now John Dalton's an interesting character. He was, I guess you could call him sort of a genius. Probably not someone who lived up to his full potential because of the lifestyle he chose, which wasn't bad, it was just sort of his circumstances. But he was one of those people who were just born really, really smart. He was very good at mathematics, and he was very inquisitive. He read a lot, he knew a lot of things. And just to give you an idea of how smart this guy was, he was teaching school, like a teacher, at like the age 13, 14, 15, and beyond. So he started teaching at a very young age. He was also a Quaker, which did temper some of his lifestyle choices, not in a bad way, but just he didn't go all out for science, if you will, because he was a staunch Quaker. Now, he started out really being a weather observer. He is well known for observing atmospheric conditions such as temperature, water vapor, all these things. And he kept notebooks. For 46 years he made daily measurements of the weather. Over 200,000 entries in his weather diaries. So he was very good at understanding the behavior of gases such as air at this time. And so one of the things that he was able to ascertain from his weather studies was that, of course, air is a mixture of different gases: oxygen, nitrogen, carbon dioxide, water vapor were really the ones that he knew about. And he asked a really important question: why don't these gases separate by density, like if you put oil into water? You know, you've done that, you've seen it. Oil rises up and the water sinks and they separate. Well, why doesn't air do that? And so he thought maybe it was because, and he drew pictures of this to kind of help work it out. Maybe they don't separate because they're particles and they're kind of zipping around, and so they don't really interact that much to separate by densities. They're kind of independently moving and bumping into things. So he starts from this developing the idea of the atom, or redeveloping it. So let me be clear, he didn't come up with the idea of the atom. He was aware of the writings of Democritus. Like I said, he was well read, so he knew the idea existed. And he was also familiar with the work of Isaac Newton. Newton also proposed the idea of particles that would help explain some of the physical phenomenon he was seeing. Keep in mind, as chemistry is developing, physics is already well on the way, and there are scientists like Boltzmann and others who are looking at some thermodynamics and trying to explain heat and temperature and all this. So Newton had some ideas about this, and so Dalton sort of put all that together and came up with the idea of atoms. Now, he also backed it up with some experimentation. So, well, he didn't do the experimenting. Dalton was not a very good experimental chemist. He was more of a thinker. And so he was aware of the experiments that other people had done. And here are some of the things he noticed. He noticed that when compounds formed, like for example water, according to the studies of others who decomposed the water to break it into hydrogen and oxygen, they noticed that the formula was always the same. It was always 2 parts hydrogen, 1 part oxygen in the same ratio. And we call that the law of constant composition. Okay, and so Dalton was like, well, if they're always in the same ratio, then the pieces that build them up must be unique to those substances, hydrogen and oxygen in this case. Another thing that he did, or he sort of summarized from the work of others, was what we call the law of multiple proportions. When he noticed that, like for example, back to hydrogen and oxygen, it could also go and form hydrogen peroxide, which is in a 1-to-1 ratio. It's the same thing with carbon and oxygen. Carbon dioxide is 1 carbon, 2 oxygens. Carbon monoxide, 1 carbon, 1 oxygen. So not only when one compound was formed, it was always the same ratio, but different elements, different substances could also form multiple ratios to make unique compounds. And again, he thought the only way this was even possible is if you had these individual pieces that constituted these substances, these elements. So from that, he put forth his atomic theory. Now I want to encourage you to watch this video. You should have already watched it, as a matter of fact, to get sort of a real good summary of Dalton's atomic theory. But for this video, we're going to skip over to my summary. I have put forth 4 postulates because I kind of condensed. I think on the video there were 6. I kind of condensed a couple of those and wrapped them all together. So this is very important for you to know. Make sure you take these down in your notes. So number 1, Dalton put forth about 1803-ish was the first written record of this. He sent some of these ideas in a letter to a friend. He says that all matter is made up of atoms, and these atoms are indivisible and indestructible. So I combined a couple of things from the video. All matter is made of atoms. That's sort of what this is all about. And then he tells us that they're indivisible. And so what he meant there was when in chemical reactions, when you put these atoms together to make molecules and compounds, that you don't break atoms into pieces to rearrange them. It's an all or none. You take the whole atom. Okay, you don't break it up. So we kind of also look at that now as what did he picture the atom looking like? And his idea was of the solid sphere. He also had no idea that the atom was made up of smaller particles like we do today. So the idea of indivisible started out meaning just it doesn't break apart in reactions, but to us now it also means you can't break it up into protons and neutrons and electrons, even though that's not what he specifically meant. Number 2, all atoms of a given element are identical in mass and properties. Summing that up, he said all atoms of an element are the same, exactly the same. And I didn't put it on here, but I kind of just, if you have number 2, the video said that one of his postulates was atoms of different elements would be different from the other elements. So that's kind of a duh to me, so I didn't put that one down. If all atoms of a given element are identical, then everything else will be different by default. So that's good. Number 3, he said compounds are formed by a combination of 2 or more different kinds of atoms. Okay, so that goes back into our law of multiple proportions and law of constant proportions or constant composition. He said, number 4, a chemical reaction is a rearrangement of atoms. That kind of goes back to the indivisible part. So it's just a rearrangement. You don't make something new. So that was the big idea in Dalton's atomic theory. This started modern chemistry. Now, Lavoisier did some things like conservation of mass in the late 1700s that kind of, nothing happens in a bubble. But the idea that atoms exist put others on a totally different course of thinking and trying to solve problems about nature. Now, it wasn't automatic. It took about 100 years to prove Dalton's atomic theory was correct and that atoms truly existed. Again, the Brownian motion that Einstein did in 1905 helped that. Now, so it was a good theory. He said a lot of great things, and it was mostly really good. There were a couple things about it that we know today weren't exactly right. The idea of the indivisible atom, not quite right. We know today that we can go inside protons, neutrons, electrons, and also fission reactions can split the atom. So chemically he was right, but physically we can actually split the atom and go inside of it. And then he was also slightly wrong about the atoms being identical for any one element. It took until probably 1930s, somewhere in that range, for us to discover the presence of isotopes and why they were unique. But today we know that isotopes exist, which means that different elements can have different atoms that differ only in the number of neutrons they have in the nucleus. But for Dalton in 1803, that was a long way away from being logical for him to come up with. So anyway, that's Dalton's atomic theory. It was very important because it laid the foundation for what would become modern chemistry. And now 100 years later, some physicists and chemists are going to start making some discoveries to give us more information about the atom. So tune in for the next video.